ClinHaem, Haematology, Demystified.
Today, we're going to do plasma cell dyscrasias, which is the last section on the malignant heme block. And hopefully the slides are moving. So yeah, it's just the hematopoiesis diagram again. Today we'll be focusing mainly on this step over here and problems to do with plasma cells. So immunoglobulin, this is the heavy chain and these two are the light chains. The heavy chain can be of either of the five types, as you know, G or A or M or E or D, so gamed. And whichever heavy chain it is, that gives you the name for the immunoglobulin. So IgG, IgA, IgM, Ig, or IgD. And these light chains can be either kappa or lambda type. Um, And of course, as you know, they're held together with the heavy chains. And this is the variable region, which is different or specific to each immunoglobulin, specific to, sorry, each to single antigen. And this is these areas are the areas that bind to antigen. And each immunoglobulin would have a different binding site. And that's what gives the immunoglobulin its specificity, which is very important. As you know, each immunoglobulin only binds to a single antigen, like a lock and key model. Now, this was immunoglobulin. Can anybody tell me what a paraprotein is? Or shall I just go?
A monoclonal protein. So all of them are the same and they're produced in excess rather than having a variety. So you've got like a malignant plasma cell that just continues to produce the one type of um, combination of heavy chain and light chain.
Perfect. Yeah. So basically is an abnormal immunoglobulin. So paraprotein is an immunoglobulin or a fragment of an immunoglobulin, for example, light chain only, and it's produced by a monoclonal clonal population of plasma cells. Now, what it means is then say, suppose I'm going to be where I know most of the people would be aware of this, but I always like to start with very basic so that if somebody is not clear, they can be sure about this. So this is a bacteria. This is not a plasma cell. This is a bacteria. So suppose if a bacteria enters the body, bacteria has millions of antigens on them. Say this is a triangle antigen, this is a circle antigen, and this is a square or something antigen. So there are millions of different types of antigens. So when B cells would be activated, each B cell would have specificity against a single antigen. So here I've just shown you three. So three B cells, each B cell that reacts against a single antigen will be activated. So for example, if there's a B cell that only reacts to triangle antigens, so that will be activated. And this is a B cell receptor on there, activated, become a plasma cell, and then this will produce lots of these antibodies that target against this. But against other B cells, which react against different antigens, would also be activated. So millions of B cells will be activated, but each B cell will have a specificity of a particular antigen, and you will have different types of immunoglobulins forming. Some immunoglobulins would be reacting to, this triangle antigen, some for circle, some for square antigen. And that's what we call a polyclonal response. Polyclonal response because different clones are being activated, so different immunoglobulins are being produced. That's perfectly normal. So polyclonal or reactive response, as opposed to a monoclonal response. So what would happen is that now there is a plasma cell, this is a plasma cell, not a bacteria. But of course, all these B cells, they will react with the antigen and then they will become plasma cells and produce the immunoglobulin. But there is a plasma cell, and each plasma cell can only produce a single type of antibody. So say this plasma cell was going to produce antibodies that were going to target against, say, a triangle antigen or whatever, or whichever antigen. So if this plasma cell becomes malignant, which basically means it's just going to make copy of itself, so clonal. So that's what malignancy is, excessive proliferation when there's no need to do so. And now all of these are derived from the same malignant plasma cell. So all of them will produce only one type of antibody, which is antibody against, in this case, the triangle antigen. So all the antibodies that they are producing are just one type. So this is called a monoclonal response, because now if you check this patient's antibodies, they will only have one type of antibodies instead of a polyclonal response. And I'll show you the immunoglobulin serum protein electrophoresis. So in this case, you will see immunoglobulin curve like this. So high, but so widespread. But in this case, if you do, you will see a sharp peak like this, depending on what's the number of the immunoglobulins. So this is monoclonal and this is polyclonal. And of course, each of the antibody will, as I say, is going to target against one antigen. So now they don't need to be producing lots of antibody to be called monoclonal. They could just be producing small amounts. They're still monoclonal. But the thing is, say by chance, if this antibody is actually targeted against an antigen. So most commonly, when this happens, this is, as you know, MGUS, which is monoclonal gammopathy of undetermined significance. So basically, a plasma cell clone. Very commonly, as people age, they will have a plasma cell clone, which is just doing, all of this and producing some immunoglobulin, which is not causing any damage, but just staying there. But say, of course, if it progresses, it can progress to myeloma. If the immunoglobulin becomes very high in quantity or starts causing organ damage, that's myeloma. But even if the amount remains small, and by chance this immunoglobulin targets an antigen that is actually a body antigen, not a random non-existing antigen, but actually a physical antigen, say on the nerves, for example. So this will cause organ damage. So this, even though the clone is small, it's producing immunoglobulins, which are small in amount, but they are against a body's antigen, like on the nerves, and this will cause neuropathy. And this is anti-MAG, IgM neuropathy, which is now termed MGCS, monoclonal gammopathy of clinical significance. So this is or other cause. So one way they can even a small clone, not present in huge amounts, can damage the body is by antigen-directed activity against the antigen. So the antibody attacking the nerve antigen that I've mentioned, or they're just being produced in an amount and they are not being cleared and they start depositing in different organs of the body. So if they deposit in different organs, that would be monoclonal immune deposition disease. If they are depositing in the body and in a misfolded fashion, that would be amyloid. But if they're depositing in the body without misfolding, then that would be just monoclonal, immunoglobulin deposition disease. And I'll show you in detail at the end, of course, what I mean. So these are all the ways in which monoclonal proteins can cause problems, or actually some of the ways. There are other ways as well. So that's very important, I thought, to mention. And if you have any questions here, I'm happy to take. Otherwise, I will move on. Good. So I hope you're clear with monoclonal versus polyclonal response. So paraprotein is an abnormal immunoglobulin protein or an incomplete fragment. So paraprotein can be a full immunoglobulin, but of course, as you know, a plasma cell is so dysfunctional that instead of producing a full immunoglobulin, it's just producing light chains, for example. So it can be full protein or a light chains only. And they are, of course, so light chain restricted. So now if the plasma cell, the monoclonal plasma cell, which is only producing one type of protein, either the full type, full immunoglobulin, or just light chains, they can only produce by definition either kappa or lambda, because that's all they know. So a paraprotein would always be light chain restricted. So it would either be kappa type or lambda type. So that's easy to understand. And then specificity, as I've mentioned, so most commonly the MGUS paraproteins, they're not specific against anything, but if they become specific to something, then that can cause problems even when it's not in the myeloma range, so to say. So this would be MGCS, monoclonal gammopathy of clinical significance, and there are various types of MGCSs now and keep being developed, and I will show you some slides for that. Now, who can tell me what are the types of paraproteins seen in myeloma? So multiple myeloma, as you know. So can you name me the types of paraproteins that you can see? So, which type based on the structure can you see in myeloma? I'm ready to write.
IgM, IgG, IgA.
Yeah, IgM. So yeah, IgA more than IgG more than IgA, and more than IgM. Yeah, is that all?
And then free light chain myeloma.
Free light chains. So basically, there's a way to classify them. So it can be intact immunoglobulins, which is IgG, IgA, IgM, or it could be light chains only. Yeah, so which is free light chains. Yeah, and this will be, of course, kappa or lambda, either way. Of course, you can have IgD myeloma and IgE myeloma as well. But of course, these two last three are rare. Most common myelomas are of this type.
And it can be non-secretory.
Definitely, exactly. That is a very good point. That's why this was going to be my next questions, or none. So these are the types of paraprotein that a myeloma can produce. So now in the none section, it can be oligosecretory. So which basically means you can still detect small amounts, say by sensitive assays like serum-free light chains or even better mass spectrometry. So the other assays that I will mention, they will miss them. But these more sensitive assays like serum-free light chain assay, which is more sensitive than the serum protein electrophoresis, or mass spectrometry, which is even better, can detect them. So they're still producing their oligosecretory. So actually, let's do it like this: oligosecretory or none. Like actually, even with those sensitive assays, you cannot find them any evidence of paraprotein in the blood or in the urine. Yes, and none are again of two types. So either when you when you do the bone marrow biopsy and you do for the plasma cells, you do immunohistochemistry or immunoglobulin, some of them would still have cytoplasmic immunoglobulin. So they would stain positive for cytoplasmic immunoglobulin, but others they would be truly non-secreting. They're called non-producers. So they would have, even when they are plasma cells and this is myeloma, but when you try to check for immunohistochemistry, even in the cytoplasmic immunoglobulin or immunohistochemistry negative as well. So the last ones are called non-producer multiple myeloma. So these are the types of paraprotein that you can see in multiple myeloma. And this is important. It is one more thing that I want to mention. But before that, have you seen this, that in myeloma, almost never you have heavy chain only. So heavy chain only paraprotein is usually not present in myeloma. But there are other diseases, which is heavy chain deposition disease, in which the plasma cell clone is producing just heavy chains without any light chains. So heavy chain only paraprotein is not present in multiple myeloma. So that's just out of for fun. But this is very important because myeloma, as you know, we have to assess the response. First of all, we have to diagnose it. So we can diagnose these from these. Not all of actually, most common myeloma is IgN, IgG, IgA, serum-free light chain. IgA myeloma most common. What am I saying? IgG is most common. Second, IgA. Third is free light chain only. So you can diagnose them, from the simple test, serum protein electrophoresis, serum free light chains. And this is again detectable pretty easily from these two tests. Problem with this one is that this is usually if it happens, the paraprotein can either be small or it can migrate to other regions, and I'll show you what it means. So among these, IgD and even IgA can sometimes be tricky to diagnose just with serum protein electrophoresis. That's why you always couple it with immunofixation and with a serum-free light chain. And I will explain what I mean, but this is important to know why you need to know which types. But of course, yeah, so these can still be detected in one way or the other from sensitive techniques, which I will mention. But the problem is, how would you diagnose these when they are not producing anything or producing very small amount? So oligosecretory, again, you can maybe detect some paraprotein from sensitive things like serum-free light chain or mass spectrometry. But the ones that are not producing anything, you cannot diagnose them from, you cannot rule out myeloma without with just doing serum protein electrophoresis, serum-free light chains, mass spectrometry, etc. You have to do bone marrow biopsy and either find there is evidence of cytoplasmic immunoglobulin there, or imaging. You have to do sensitive imaging. So these ones would require imaging to diagnose and monitor to see if there are any changes present. This is, of course, not myeloma, so we will not discuss that at the moment. So these are the caveats of all of the things I've mentioned. Now, lastly, what I wanted to say is IgGs, IgM and IG. Oh, no. Now, IgG. So, this is the immunoglobulins that I was showing you. This is how IgG looks like in very simple form. And this is how it floats in the blood, so to say, as well. IgA, it usually, as you know, this is not an accurate diagram, but it floats as a dimer. So IgA is bigger than IgG. IgM, as you know, 5, 2, 3, 4, 5. Yeah, that's not very symmetrical, but you get the point. So IgM floats as a group of 5, so pentamer. So IgM is the biggest, so to say. And that is why if you have a person with same amount of paraprotein, say 10 grams of IgG, 10 gram of paraproteins. So one patient has IgG type, other has IgM type, IgA type, and the last one has IgM type. So whose viscosity is going to be the highest? Clearly, IgM type with the same level of paraprotein, his blood would be more viscous because these paraproteins are actually bigger. Second in line, this patient's viscosity would be second in line, and these likely to have the least of the plasma viscosity. So 10 grams of IgM is likely to give you the thickest blood, so to say. This is second in line, and this is third in line with the same amount of paraprotein. So that's important, and that's why, of course, you see hyperviscosity very commonly with IgM, and second in line IgA. IgG you can see, but you have to have really high paraprotein to give you hyperviscosity syndrome and things like that. Okay, so any questions up till here? These are pretty basics that hopefully help if you don't know them, but most of you know, I know. No questions? Or just catching up on your sleep or something? You guys okay?
No, all good, thanks.
Good. Okay. Yeah. So how do you test paraproteins? So instead of quizzing you,
Thank you for watching. Stay tuned for more.